Deep learning has revolutionized artificial intelligence, but at a steep cost. The backbone of modern neural networks is the matrix multiplication, a computation that drives both performance and energy consumption. And while GPUs have enabled breakthroughs in vision, language, and robotics, they come with a heavy price: astronomical energy use, extreme hardware costs, and severe supply constraints. These limitations make deploying AI on edge devices, think smart sensors, wearables, or remote IoT nodes, practically impossible for most. But what if we could eliminate multiplication entirely? What if the next generation of neural networks didn't rely on floating-point arithmetic at all? Inspired by the elegance of biological nervous systems, we propose a radical new architecture: Neuro-Channel Networks, or NCNs, a fully multiplication-free neural network that learns complex nonlinear patterns using only addition, subtraction, and bitwise logic. Let's unpack how this works. In artificial neural networks, each neuron computes a weighted sum, the dot product of inputs and weights. That multiplication is computationally expensive. It requires floating-point units, consumes significant power, and dominates the silicon area in accelerators. But in biology, synapses don't perform arithmetic. Instead, signal transmission is regulated by physical constraints: ion channels that open and close based on voltage gradients, and neurotransmitters that modulate synaptic strength through chemical signaling. NCNs mimic this biological mechanism. Here, weights are not multipliers, they are physical channel widths. Think of them like the diameter of a pipe. If the input signal is small, it flows freely. If it's large, it gets capped at the channel's limit. This is implemented not with multiplication, but with a simple minimum function and sign preservation, a process that can be executed in hardware with just a few logic gates. Mathematically, the output of the channel is CXW equals SGN X min XW. This is a dynamic signal clamp, no multiplication, just comparisons and conditional selection. But here, S the key insight. In real brains, even when a physical channel is closed, signals can still pass via chemical pathways. So we introduce a second mechanism, the neurotransmitter bypass. This is a learnable secondary path governed by a second parameter, N, that acts like a chemical modulator. It creates a parallel signal flow, allowing information to leak through even when the channel is saturated. The output of the bypass is BXN equals SGN X min XN. This isn't just a backup, it's a learnable regulator. When the channel width becomes too small, the neurotransmitter path keeps the gradient flowing, preventing the dead gradient problem that plagues other low-precision models. Now both signals, channel and bypass, are summed together in the cell body, mimicking spatial summation in biological neurons. But here, that's where it gets clever. In deep networks, summing many inputs causes signal variance to explode. To prevent this, we apply a static scaling factor, 1 over the square root of the input dimension, just once per neuron. So the final output becomes y equals sigma c plus b slash square d plus b. This normalization is O1, a single scalar operation, while the thousands of synaptic computations remain entirely multiplication-free. And because we're only using addition, subtraction, min operations, and sign checks, this entire forward pass can be implemented with bitwise logic and integer arithmetic. No floating-point units. No multipliers. Just simple, efficient logic. Now, can such a system learn complex tasks? We tested it on 2 classic nonlinear problems, XOR and the 3-bit majority function. XOR is famously impossible for a single-layer perceptron. It requires nonlinear decision boundaries. Yet our NCN, using a 2 right arrow 4 right arrow 2 architecture, learned the entire truth table with 100% accuracy using standard backpropagation. The network didn't just classify correctly, it learned a nonlinear decision boundary, separating 0 and 11 from 1 and 10, all without a single multiplication. Then we went further, the 3-bit majority function. Given 3 inputs, output 1 if 2 or more are 1. This tests threshold logic and information aggregation. Again, the NCN, using a 3 right arrow 8 right arrow 2 topology, achieved 100% accuracy across all 8 input combinations. This proves a fundamental point. You don't need multiplication to build nonlinear expressive models. The interaction between channel saturation and neurotransmitter modulation creates rich, nonlinear transformations. So why does this matter? Because it redefines what's possible in AI hardware. Standard deep learning demands GPUs, expensive, power-hungry, and scarce. But NCNs can run on commodity CPUs, ultra-low power microcontrollers, or even custom neuromorphic chips. The computational graph is so simple that it can be synthesized directly into hardware using logic gates. No need for floating-point multipliers. And this isn't just theoretical. We've already laid the groundwork for fully multiplication-free training. Our future work will extend the paradigm to optimization, replacing gradient updates with sign-based or additive updates, like sign-SGD, so that both inference and training operate entirely on bitwise operations. We're also scaling up to deeper architectures, testing NCNs on MNIST and CIFAR10, to see if they can match CNNs in performance while using a fraction of the energy. And yes, we're designing real hardware. FPGA implementations and ASIC co-designs are underway to measure actual power consumption per inference. Early estimates suggest orders of magnitude reduction in energy use compared to traditional DNNs. This is more than an architectural tweak. It's a paradigm shift, one that aligns deep learning with the physical reality of biological computation. Instead of forcing artificial neurons to mimic arithmetic, we're building them to mimic biology. Neuro-Channel Networks represent a path forward. AI that doesn't depend on expensive hardware, but runs everywhere. On batteries, on sensors, on devices we don't even think of as computers. The future of AI isn't just smarter, it's simpler, leaner, and more efficient. And it starts with a single idea. What if we stopped multiplying and started flowing?